So we didn't get a chance to look at the graph of e to the x and compare that with the graph of 3 to the x. So let's take a look at that one. So let's open our little calculator here. So 3 to the x, again, we saw these graphs last time. You have your horizontal asymptote at the x-axis, our y-intercept at 0, 1, and of course, this is an increasing function. Now, when we're talking about e to the x, I'm actually not sure if this is going to work. But we're going to try. If not, we'll have to use Google to help us out. Oh, it worked. So you will notice that they are kind of similar, but not exact, right? Because the one in the red is our 3 to the x function. 3 to the x is going to be a slightly larger number than e. What's the approximate value for e? You should just be able to do e raised to the power of 1. Yeah, 2.718, and it keeps going, right? So let's say it's about 2.71 or 2.72. So that has a little bit of a smaller base than 3. So it's not going to be quite as steep in its growth as the 3 to the x function is going to be. But obviously, it still gives us a pretty good approximation of what our e to the x function should end up looking like. And of course, if you zoom out, they look a lot more similar, except when they start growing on this part right here. Okay, so that's kind of what I wanted to do since we didn't get a chance to look at this last time. Now let's get into our radioactive decay model here. Okay, so you should notice that this radioactive decay model, A equals A sub 0 e to the RT, looks a lot similar to our continuous compounding formula. Here we've got A equals P times e to the RT. So we're literally just taking that P principal value and replacing it with A sub 0. So it's going to be pretty much the same kind of model, with the exception that here, instead of talking about growth, we're talking about decay. So just for the variables here, the A variable stands for amount of radioactive substance remaining after T years have passed. A sub 0, of course, would be what was the initial amount present, and your R represents your annual rate of decay. So how fast is this radioactive material decaying each year? Now, one of the big differences between our compound interest formula and this radioactive decay formula is we are talking about decay, which means our substance amount is going down, which means our rate is going to be a negative number. In compound interest, and especially the continuous compounding formula, we know our rate is positive since our investment grows. So here, our rate will be negative. Okay, and then they're talking about this formula is used to determine the age of ancient objects like bones, campfire charcoal, meteorites, and we'll actually look at more examples of this in 4.4 after we have talked about logarithms in our next section. So let's go ahead and take a look at this example here. So they want to know if the amount in grams of carbon-14 present after T years is given by this formula, A equals 2.9 e to the RT, where our rate of decay is negative 1.21 times 10 to the negative fourth. Then they want to know what was the initial amount present and what amount will be basically left after 6,500 years have passed. So they're asking us to find the initial amount and what amount we have left over after 6,500 years. So let's see what we have here. A equals 2.9 e to the power of RT. They're telling us the rate is negative 1.21 times 10 to the negative 4. And the two questions they're asking us is to find what was the initial amount. So what would be the initial amount? And what amount would be present? So find the amount if your time is 6,500 years. So two questions. Let's start with that first one. So when we're talking about initial amount, basically when the substance existed, maybe whatever years ago, at time 0, what initial amount did we have? So anytime they're asking you to find the initial amount, that means you're basically looking at the beginning of this time frame, which would be at time 0. So we're actually going to take our formula that we are given and set it with time equal to 0. We have a rate of negative 1.21 times 10 to the negative 4, and our time is 0. So what happens when we multiply anything with 0? It becomes 0. So your exponent will end up becoming 0 since we're multiplying r times t. And what does 0 exponent rule tell us? Any base raised to the 0 exponent will become 1. So you actually end up getting 2.9, and that e to the 0 part of it will end up becoming 1. So that actually means at the initial time, the initial amount of this carbon 14 is actually that 2.9 grams. And you know, that's pretty standard because when you're talking about radioactive decay, in this little formula, that 2.9 will always represent what the initial value was when we got that substance. And in this case, the initial value for carbon 14. So that was the first part. Then they're asking us to find after 6,500 years. So this is so that would again be A equals 2.9 E raised to the power of R, which R again is negative 1.21 times 10 to the negative 4th, and our time is now 6,500 years. Now be careful the way you type this in your calculator, because this quantity here should be in the same parentheses. You cannot have two different parentheses like I have written out on the paper. So you'll do 2.9 times your shift or second ln key to get to the E, and then in your exponent you will type all of this as one parentheses. So you can start with negative 1.21 times 10 to the negative 4 times 6,500, and then close your parentheses. So be very careful of how you type this guy in. And once you do, what kind of answer do you come up with? $1.32. 1.32. This is going to be a pretty long number. We'll just round it to 1 decimal place. So after 6,500 years, there will only be 1.3 grams of carbon 14 left behind in, I guess, whatever that object was. So here, since we have that negative exponent, that's why we started out with 2.9 grams, but now our number has gone down to 1.3 grams. If that R was positive, then you would have seen this number grow. But since we're talking in terms of a decay model, carbon dating, that negative will make this amount go down. Okay, so that's really the only difference between having a positive exponent on E and having a negative exponent on E. Or for that matter, any exponential function. Okay. Questions on 12? Alrighty, that's pretty much what we had left to talk about in 4.1.